Welcome to this explainer. We're jumping right into the intense, high-stakes engineering required to maintain, repair, and eventually lay an offshore well to rest. So let's set the scene here. Imagine trying to perform heavy maintenance on a degrading structure thousands of feet underwater. We're talking about reservoirs that naturally sit at pressures from 3,000 to sometimes over 15,000 psi. How on earth do you safely intervene in an environment that volatile without losing control? And more importantly, how do you do it without having to completely kill the well's production first? To wrap our heads around this, it really helps to think of the well as a patient. Just like a person, a heavy steel and cement well degrades over its typical 25 to 30-year lifespan. Way down in the dark, that production tubing is taking a constant beating from the full force of reservoir pressure, nasty formation acids, and highly abrasive sands. Over the decades, packers leak, tubing joints fail, sand builds up at the bottom of the hole, and eventually, this patient needs some serious medical intervention. When that time comes, engineers basically have two routes. They can go with wireline operations, which you can think of as a minimally invasive routine checkup. It's just a thin steel cable and small tools going into a live well to do routine stuff like test a safety valve or clear a minor blockage. Or they have to perform a workover. And a workover is the equivalent of major open heart surgery. It requires heavy intervention, like replacing the entire production tubing string, setting a new packer, re-perforating in a totally new zone, or chemically stimulating the rock reservoir itself. A workover is a massive, highly complex undertaking. It means re-entering a completed well using a full workover rig, which is essentially a portable version of a main drilling derrick, or a specialized coiled tubing unit. For the most serious mechanical workovers, like replacing damaged production tubing, engineers actually do have to kill the well first. They pump heavy brine downhole to overbalance the hydrostatic pressure of the formation, making it safe enough to pull the Christmas tree and start the surgery. Now, quite often, the diagnosis that triggers this heavy intervention is just incredibly poor hydrocarbon flow. You see this a lot in formations with very low permeability, like the tight chalk formations in the Gulf of Mexico or the North Sea. The oil or gas is absolutely down there in the rock, but it just can't flow easily to the wellbore because the rock structure is way too tight. It's exactly like blocked arteries restricting blood flow, and to cure that, you need an extreme surgical solution. That solution is usually hydraulic fracturing, or fracking. Let's walk through the physics of how this actually works. First, a fracturing fluid, usually a specialized gel or slick water, is pumped down the well at just incredibly high rates and pressures. This hydraulic pressure is so intense that it literally cracks the solid reservoir rock. These fractures propagate outward from the wellbore, completely expanding the drainage area. Then, a crucial solid material called proppant is injected to keep those brand new fissures open. This proppant is absolutely key to the whole operation. It's made up of small sand grains or artificially manufactured ceramic beads that are mixed right into the fracturing fluid. See, when the operation finishes and the fluid pressure drops, that heavy rock naturally wants to snap right back shut. But the proppant gets trapped inside, physically holding the fractures apart. It basically creates a permanent high permeability highway for oil and gas to flow straight into the wellbore. But what if the issue isn't naturally tight rock? What if the flow channels are actively blocked by damaging scale deposits or clay? Well, for that, engineers use a chemical treatment called acidizing. Hydrochloric acid is pumped into carbonate reservoirs, like limestone, to dissolve the rock along natural fractures. If it's a sandstone reservoir, they use a mixture called mud acid, which is specifically designed to dissolve clay damage and scale. The acid literally eats away the blockage, widening the channels and improving connectivity back to the well. Delivering those powerful acids and carrying out these intensive workovers brings us to one of the most revolutionary tools in offshore engineering: coiled tubing. Now, unlike a traditional drill string made of individual 30-foot threaded pipe joints that have to be screwed together one by one, coiled tubing is exactly what it sounds like. It's a continuous, unspooling snake of flexible steel. The surface setup required to pull off this physics-defying operation is just incredible to look at. It starts with this massive reel where the steel tubing is coiled in continuous lengths. We're talking up to 20,000 feet of pipe. The tube goes up and over a curved guide called the gooseneck, and then an injector head physically straightens the steel and pushes it down through a blowout preventer directly into the Christmas tree. Once it's pushed down whole, this flexible steel tube reaches thousands of feet deep, navigating all the way to the exact target zone.
Because it's a continuous hollow tube, it acts a lot like a giant intravenous line, delivering fluids or mechanical tools precisely where the ailing well needs treatment the absolute most.
The versatility here is just amazing. Coiled tubing can run downhole tools for logging or perforating the casing. It can pump acid, scale dissolver, or even cement directly to the target zone. It can perform a nitrogen gas lift, which means pumping high-pressure nitrogen gas down the tube to purge heavy liquids from a well that has loaded up with water and completely stopped flowing. And if you attach a motor and mill to the bottom, this flexible steel snake can literally drill right through thick cement plugs or hard scale deposits.
But here's the ultimate engineering feat of this entire system. Coiled tubing can do all of this while entering a live well. Using a highly specialized pressure control assembly, similar to wireline setups, engineers can insert this tubing without having to kill the well's hydrostatic pressure first. This completely avoids that heavy brine displacement we talked about earlier, which drastically reduces intervention time and saves an absolute fortune in costs.
Of course, no matter how much surgery or stimulation we do, every single patient eventually reaches the end of the line. So, let's look at the final stage of the life cycle: permanent well abandonment. After 20, 25, or 30 years of productive life, an offshore well's reserves are fully depleted. But abandonment in this industry isn't just walking away and leaving a pipe in the ocean. It is an intensive, environmentally critical process of permanently sealing all potential flow paths from the reservoir to the environment.
Think of this as the well's systematic hospice care. First, thick cement plugs are set at multiple intervals inside the well across all the hydrocarbon-bearing zones. Next, any permeable formations are completely sealed off. Then, a massive final cement plug is set right at the mudline, the seabed itself. Once those plugs are confirmed solid, the steel casing is physically cut below the mudline and the entire wellhead structure is removed. Now, why is this executed with such extreme rigor? Because once abandoned, that well has to maintain its structural and environmental integrity for the indefinite future. In fact, in some regulatory frameworks, the baseline goal is for those seals to hold perfectly for a staggering 1,000 years. Let that sink in for a second. 1,000 years. Which leaves us with a monumental challenge to ponder. Abandonment is a massive and rapidly growing part of the offshore industry's workload. As the first generation of legacy fields in the North Sea and the Gulf of Mexico reaches the end of their productive lives, thousands of deepwater structures are entering this final phase. So how will the engineering community safely manage this massive global cleanup while ensuring environmental perfection for the next millennium? It's a fascinating, urgent question that the industry simply has to answer in the coming decades. Thanks for joining me on this explainer. I hope you walk away with a newfound appreciation for the incredible engineering it takes to keep offshore wells alive and safely put them to rest.